So, until now all the discussions we have had with different scenarios that we looked into, they were in the context of single particle dynamics. So, we have explored aspects of shape, we did spherical particles exactly, we did anisotropic particles which were using slender body theory. So, and then we also saw that there is a general method for addressing arbitrary shape which is using boundary integral method. So, we explored different details of shape. Obviously, different big background flows, we have done translation problems, we have done rotation problems, we have done linear flow problems. So, we have looked at different kinds of aspects of flows that played a role. We explored aspects of finite Reynolds or fluid inertia, and we saw what is the consequence of having fluid inertia. We also explored what is the consequence of having particle inertia, basically writing down an equation of motion for a particle which necessarily is not having zero acceleration or deceleration. We also saw the consequence of thermal fluctuations, which is to say that Peclet is finite. So, we have done a variety of these things for single particle dynamics. We have gone through some of them and we have computed things like, from this we have computed quantities like drag, torque, suspension viscosity and more. But whatever we did, they have always been focused on single particle effects. So, the point being that there is no aspect of hydrodynamic interaction between the particles. So, the particles are non-interacting. So, we can study them in isolation. So, today's lecture we are going to go a bit beyond and touch upon something that is a very important problem or important aspect to study in particulate flows, which is regarding hydrodynamic interactions. Now, hydrodynamic interaction plays an important role in a variety of different things, whether you are interested in things like suspension viscosity or the broad area of rheology. You are interested in settling behavior. So, you can think of a collection of heavy particles settling in a fluid. So, as there is a scenario where they are sufficiently concentrated, the settling behavior is going to be influenced by interaction. You can have some collective behavior in a system due to interaction. In low Reynolds number flows, we have seen that the disturbance actually decays very slowly. So, if you remember, if it is a translation problem, what is the decay of disturbance? How rapidly does the velocity decay for a translation problem with distance? 1/r. The velocity disturbance due to an object that is translating is decaying inversely with the distance from the particle. So, it is a very slow decay. 1/r is not a very rapidly decaying function. If it was a neutrally buoyant particle in some linear flow, then that decay was 1 over r square. So, when you have such long range velocity field for particles, that can lead to, in scenarios, a collective behavior where they can talk to each other even though they are sufficiently far apart, because the velocity field is decaying off in a really slow manner. You can also have aspects of coagulation that is driven by interaction. Like if you want to understand how would two particles come together and aggregate. So, aggregation or coagulation, that is basically a problem of studying interaction of particles, that what would drive them together, what would bring them together. Now, this in general, like if I am not saying anything more, is an extremely difficult many body physics problem. So, you can imagine that you have a whole bunch of particles. I am drawing them as a spherical particle for just a reference, and all of these are actually moving while they try to interact with each other. So, this is, forget theoretically, this is a computationally also a very challenging problem to do. It is not something that is in any sense trivial. So, you can then say, what about if I focus on pairwise interaction? So, pairwise interaction means that at a particular time, I am basically only trying to understand the interaction of a pair of particles. So, this is a scenario where you can think of that the system is not necessarily infinitely diluted, but it is still not concentrated enough, where at a given instant of time there are only two particles in pairs which can interact. The probability of a third particle engaging in that interaction, or more than 3 particles engaging in an interaction, becomes extremely small. And how do we decide that? That is decided on the volume fraction or the number density of the particle. So, as you keep increasing the volume fraction, 3 particle interaction, like 3 particle participating in an event, something like this, becomes likely. So, we are looking at a concentration at which such 3 particle encounters or more than 3 particle encounters are extremely unlikely. We are only looking at pairwise interaction. So, even if you say we are trying to focus at pairwise interaction, this is again a formidable calculation. And if you want to make your life further simplified and you consider this to be not just any particle, but 2 spherical particles. A single sphere is the hallmark of what we did in Stokes flow calculation, right? We studied our single sphere calculation. So, now from a single sphere, if we are doing 2 spheres, it appears that we have done just one more additional particle in the problem, but even just with this one additional particle problem, if you are doing this kind of an interaction calculation, it is quite challenging. It is computationally challenging, it is theoretically challenging, but it is a problem that is of vast importance in varieties of different things. For instance, if you remember, you had calculated what was the suspension viscosity. This was the Einstein calculation. Now, you can ask the question that this is obviously the very dilute limit. What would happen if it no longer remains that dilute? Then the next term is going to be an order phi square term. Phi is the volume fraction. But what is that coefficient? That actually depends on what is the kind of background flow. See, when you did the suspension viscosity calculation and you found the coefficient to be 5/2, did you actually choose the kind of background flow? We said this was a linear flow calculation. Go back to when we did the suspension viscosity calculation. We computed the relation for the particle stress in terms of the single particle stresslet. And then when we substituted for the single particle stresslet, did we ever specify whether it was a simple shear flow, whether it was a planar extensional flow, whether it was a uniaxial compressional flow? Did we specify what kind of a background linear flow it was? We never did that, right? The relation between stress and the rate of strain, which was multiplied by the suspension viscosity, for Einstein's calculation doesn't require you to specify what kind of linear flow you are interested in. You can choose all kinds of possible straining motion and you will get the same answer 5/2 But if you are asking the question that what is the next correction to the volume fraction due to volume fraction to viscosity, that is going to require you to do a pairwise problem. You need to solve the interaction of two spheres, and there the answers actually crucially depend on whether you are doing a simple shear problem, which means you have a flow field which is rectilinear where the velocity field increases perpendicular to the direction of motion, or you have, let us say, a stagnation point flow where the velocity field is a planar extensional flow, or you can have a flow field that is uniaxial compressional flow, which means that there is a compressional axis, imagine along the z axis, and in the xy plane it is an extensional flow. So, it matters what is your background linear flow in order to find this pair interaction calculation. So, it is quite hard and it is also quite detailed as a calculation. So, what we will pick up today is something that I am not trivializing the difficulty of that problem, but we can do something without getting into the whole gory details of the calculation. That is the problem of a pair of sedimenting particles. I have two spheres, I am focusing right now everything for a spherical particle, and then when we do these calculations we are going to, I will make a point regarding what happens when the particle is not spherical. So, I have a spherical particle, let us call this particle 1, this particle 2, they are not necessarily the same size, A1 and A2, and they are falling under the action of gravity. So, if you have to treat this problem in isolation, isolation means the spheres do not interact. What is the settling velocity of sphere 1 and what is the settling velocity of sphere 2? So, I will make it a little general by saying that there is a force that is acting, here it is obviously gravity, but let us say there is a force F1 acting on, I will call this external. There is an external force that is acting on sphere 1, which is F1. There is an external force that is acting on sphere 2, which is F2. F1 and F2 for this problem is the weight of the sphere. So, if I know what is F1 and F2, what would be the settling velocity? F1 6 pi mu A1, right, and what is U2? 6 pi mu A2, right. This is something we know quite well, right. This is basically relating the external force to the hydrodynamic force or the drag force, and from that we find out what is the velocity of sphere 1 and sphere 2. Now, the question is if I want to write this in terms of a mobility form, I can write this as m dot F1, where this mobility is the identity matrix by 6 pi mu A1. Is that okay? So, for a spherical particle, the mobility tensor is basically the Kronecker delta multiplied by a factor of inverse of 6 pi mu A1. If this was not a sphere, if this was some other object, the mobility tensor need not be isotropic. And we already know this, right? When you did this problem for a slender body, then the mobility tensor was something that was axisymmetric. It had a form that was like delta minus PP plus PP, right? So, the point I am trying to make here, that for every shape, I am going to do this for a sphere, but I am just giving you a small detour here, that for any other shape, this expression does not change, this expression stays exactly the same. That is just the definition of mobility, that the velocity of the particle is going to depend on the external force via the mobility tensor. If it is a spherical particle, the mobility tensor is isotropic. If it is not a spherical particle, the mobility tensor will take the corresponding form relevant to that particle's geometry. This relation comes from the linearity and instantaneity of Stokes flow. This is what we learned when we discussed resistance and mobility form, that you can relate the instantaneous drag to the instantaneous velocities of the particle. Obviously, when we went to unsteady Stokes, you saw this broke down, because there you had a history term. But right now we are focusing on the steady Stokes equation, which means at a given point in time, the force acting on the particle depends on the velocity of the particle at that point in time. And so, the inverse statement is, the velocity of a particle at a given instant in time depends on whatever is the force that the particle is experiencing at that instant in time. Okay. But this object is an object that is purely a function, I mean, if you take out the mu factor from there, it is purely a function of geometry, the size and the shape. For a sphere, it takes an isotropic form, but if it is not a spherical object, if it is something that is non-spherical, it will take a more complicated form. Okay. Similarly, the velocity of the second sphere we could write in this particular manner, where m22 is I by 6 pi mu A2. So, the reason why I am doing all of this is that this statement is a very general statement. These two statements are applicable for any particle. It need not be sphere. The mobility tensors will take certain forms depending on what particle you are studying. So, the mobility tensor captures the aspect of particle shape and particle size. So, now when you say they are interacting, the linearity of Stokes flow tells us that the velocity of particle 1 is going to depend on the force experienced by particle 1 as well as the external force experienced by particle 2. That is the statement of Stokes flow, that I have two objects, need not be sphere, any two objects. if I am saying that these two objects are under the action of some external force, then the velocity of any of these two objects would depend on the force experienced by each of these objects. The form of the mobility tensors as you change the separation is going to obviously be a function of that particular separation. So, what form it basically takes as you are trying to bring them closer, that depends on whether you are doing a problem where you are trying to apply a same force and trying to find the velocity, which is what the mobility calculation is. So, in that particular case we will look into, because right now there is nothing that can tell us exactly that how should the mobility behave as the separation goes to 0. One thing we can say with some degree of confidence is, if I am keeping the force fixed, then as the two particles are brought closer, so it depends on the detailed nature of the boundary condition. If you have two spheres where it is a no slip, no penetration boundary condition, then the mobility that you have between the two particles, that would have a certain way in which it will go to 0. The mobility will vanish as you bring them closer. In contrast, if you imagine that they were drops, there also it would vanish, but it would vanish in a different rate or a different way. So that is a question which you can answer when you know a little bit more regarding the exact nature of the boundary conditions between the two objects. So what we have now is this particular general form. Now how do I go about finding this? That is the question that we are interested in today's lecture. That how do we find these mobility tensors? Now as I have already said, this is not any trivial calculation. Even if you bring it down to just two spherical particles, it's still a very complex exercise in order to find these mobility tensor components. So what we will do today, in today's lecture, we are going to focus on a method that is owed to Smoluchowski, that is known as method of reflections. Now what does method of reflection actually say? You have two spheres, sphere 1, sphere 2. Now sphere 1, if you view sphere 1 in isolation, which means you forget that there is ever a sphere 2, then sphere 1 is translating with a velocity which is u1, and it creates a disturbance which is your usual flow field due to a translating sphere. We know this quite well, right? If there is a translating sphere, it creates a certain flow field. There is a Stokes-Lett part and then there is a potential dipole part. So now if you think of sphere 2 is in the flow field of sphere 1. So sphere 2, just by virtue of being in sphere 1's flow field, it has to move, right? What sphere 1 is doing, it is churning the flow. As it churns the flow and creates this disturbance is going to go and push and deflect what sphere 2. So imagine sphere 2 was not moving, sphere 2 was just stationary and stagnant. As sphere 1 moves, automatically sphere 2 is going to get a kick and it will move. In the same way, you can argue that when sphere 2 is moving, it creates its own velocity field in which sphere 1 is embedded. So if you know that sphere 2 is translating with some velocity, it creates its own velocity which is going to disturb sphere 1 and make it move. That is the essential idea, that the motion of sphere 2 is going to translate sphere 1 and the motion of sphere 1 is going to translate sphere 2. But then when sphere 2 creates the disturbance field, so this is a disturbance field that is created by sphere 1, right? This is the velocity field that is created by sphere 1. That velocity field is influenced by sphere 2, because sphere 2 has done two things. Sphere 2, by being in the velocity field of sphere 1, it has started to move, and it is also creating it's changing the stress. It is translating and it is also changing the stress. So what it does is, what was the unadulterated velocity field of sphere 1 gets altered. So then there is a feedback. The feedback is sphere 1 now sees its own disturbance getting affected by sphere 2 coming back to itself. So that is the reason why we call it as a reflection. Like if you imagine drawing two surfaces, and imagine there is some ambient flow. In this problem there is no ambient flow, but imagine that there was an ambient flow, and this is particle 1, this is particle 2. So the presence of particle 1 is going to create a velocity field 1. The presence of particle 2 is going to create a velocity field 2. The velocity field created by 1 is going to influence the particle 2, right? And then this is how it goes further. That's why I am using the word reflection, because it doesn't stop, it doesn't terminate. The way we are trying to understand this, that this is not a terminating exercise. This exercise is where you are trying to think of it in a sequential manner. But you have to keep it in mind, this is not something which is like one step at a time or one reflection at a time. All of this is happening exactly simultaneously. It's your way of understanding that how each object influences the other object. Because ideally what you would have wanted to do is go back to this particular problem and solve this problem using some method. You solve Stokes' flow, you apply the no slip, no penetration boundary condition, and you get back your answer. Now that sounds fairly straightforward, but it is not that straightforward, because you would have to either solve this numerically or you have to use some very special analytical methods to solve it. And even those very special methods analytically, they are going to fail the moment you move away from spherical shapes. If I say this is not a sphere, one of them is not a sphere, one of them is like a spheroid, it's basically something that is slightly more elongated, then all those fancy methods are not going to work. But the idea that we are trying to understand here, this idea can actually be applied to also a lot of different shapes. It is an idea which is obviously works very well when the two spheres are sufficiently far apart, or the two particles are sufficiently far apart. When you start bringing the particles to distances comparable to their sizes, then you need to do a lot of these reflections. See, finally this is now a question of how many of these calculations do you need to do. So today's lecture we are only going to do one reflection. I am not going to do more than one reflection, and you will see already that one is sufficient to understand few things. But if you bring them closer, you are not going to find answers accurately with one reflection. You might need 5 reflections, you might need 10 reflections, depending on how much closer you have brought them. So this approach is ideal to get a feel for how two objects are interacting mediated by the flow. So as when we will write down, you will see that this is a method which is applied based on the far field interactions. So obviously the question is, how many of these reflections do you need to keep? Now the answer of how many you need to keep, that depends on how far are they separated. So it's like doing a series summation. Do you truncate the series after 2 terms, after 5 terms, after 50 terms, after 1000 terms? That depends on how much closer you have brought it in. So that you can come up with you have to prescribe a tolerance, that does the result actually within a certain tolerance stop changing after you add a few number of terms based on the separation. So you can basically come up with, so typically when you are looking at distances which are tens of particle diameter, like the separation is around, let's say 10 particle diameter, 20 particle diameter, the first few reflections, 2 reflections or so, would be sufficient in terms of understanding what is going on. So now you have to think, so it's an interesting point. So now you have to think, what is it for, what is happening for the second particle? What is it that you are fixing? What is it that you are changing? The picture that I have drawn here, what is it that you have fixed? What is fixed and what are we finding?
The motion of the second particle are fixed.
No, in this picture, the problem that we are trying to do, what is fixed and what is it that we are trying to find?
The velocity separation.
So the force is, the force is fixed, right? The force is fixed. We are trying to compute the velocity. So this is a classical mobility problem. Now, what would be the equivalent resistance problem?
Like when the velocities are fixed, we are trying to find a force.
Right. So what would be an example? Imagine the simplest example. You keep the 2 particles fixed and you have a flow past the 2 particles. Then what are you calculating? You are calculating drag. Right. You have 2 spheres which are glued in space. Can you think of a place where you think this thing will happen? Where the spheres are fixed in space? Flow past a sphere, yes, but when you are thinking of a lot of spheres which are present and they are fixed in space. What reactor? Packed bed. So any kind of packed bed or porous medium, fixed bed, packed bed kind of thing, where you actually have the objects are stationary and you have flow through the stationary obstacles. The obstacles are not mobile. So because the obstacles are stationary, the velocity is fixed, which is 0. The velocity is held 0 for all the objects and you are computing the force on the particle. So that is a resistance calculation. Now what you are saying is a mixed problem, because one of the sphere is held fixed, the other is free to move, which means for the sphere which is mobile, it's a mobility problem, because it is experiencing only its own self weight. It is not experiencing anything else, whereas sphere 2 is held fixed. So whatever you do, it cannot move, you are fixing its dynamics. So then the drag force or the total force on the object is going to change. So it's a mixed problem in that sense, and you can do it in the same manner. You can basically now ask the question that I have fixed this particular, it's like the motion of a sphere near a wall. If the second sphere was infinitely large, it's like the settling behavior of an object next to a wall. So now you can imagine that the velocity field of sphere 1 gets reflected by the wall and comes back. So nothing is going to change the dynamics of sphere 2 because it is anyway stationary. What will change is the force acting on sphere 2. That if you were to measure that what is the drag force on the wall or the second sphere, that is going to change with every reflection. But the dynamics cannot change because you have already said it is stationary, it is not moving. So for sphere 1, you are going to have the reflection at every instance changing its, updating its velocity.
So the first time step,
yeah, there is no time step. There is no, this should not be seen like a sequence of reflection. It's not a sequence of reflection. This is all happening together instantaneously. There is no time. It's not like first reflection, then there is a second one, then there is a third one. It's not. What is that? What is the speed with which disturbance propagates in Stokes flow? Infinite, right? So there is no speed here, finite speed with which 1 and then 2 then 3. It's all together. It's our way of understanding what is going on by considering the interactions as first, second, third, fourth, etc. deflection. You have a solution. That's why I said, if you could, you would have gone ahead and done this calculation. If you do this numerically, then you are basically saying at a given instant of time, if the two spheres are located at a particular configuration, what is the velocity with which they are moving, or what is the drag force on these two spheres, whatever is the question that you are interested in. That is the calculation at a given instant in time.
So numerically, when we are solving this problem, if we consider the scenario where the first particle starts to move,
right,
due to the influence of the first particle, then the second particle starts to move.
It is not that way. It is not a, it's not a temporal evolution. That's what I'm trying to say. There is no such temporal evolution in this problem, because the governing equation still is minus grad p plus mu del square u is equal to 0, subject to the incompressibility condition. This is not changing. So there is no such temporal evolution in the problem. If you were to include the unsteady term, that is a different story. But when you are doing this, whatever we are describing, there is no temporal evolution, there is no sequence of events. It's not like one causes the other. None of these are statements that are true. Don't think of it as a causal problem or as some direction of time kind of a problem. It's all happening together. You are trying to understand that the behavior can be dissected as an interaction that is happening based on the first reflection, an interaction that is happening based on the second reflection, or an interaction that is happening based on the third reflection. So you are trying to basically separate out the full picture into these individual pieces. This is what we are basically doing by saying that this is something that makes sense only when the separation is large enough. When the separation basically becomes, see, the entire point is resting that once they are far enough, you have solutions where there is a decaying part that goes as a certain power of r, and then there are other pieces which decay faster than that. So you are doing this for sufficiently large separation. Once the objects are close, then this kind of a dissection is not helpful. So the reflection approach that we are discussing is something that is basically motivated by the fact that I know what happens when I am in isolation, right? I have some understanding. I am sitting here in this chair, someone suddenly opens the door of this room, I will have a certain feel for, just without even opening my eye, the gust of air that comes in, I will feel that gust of air and I will have a feel of what is happening. This is very different from when there are like 5 people almost crowding around me and trying to move. So this is trying to just get the first level picture correctly, saying that when separations are significantly large, you can start off by thinking of this as an interaction where as if particle 2 is just experiencing the velocity field of particle 1 and particle 1 is experiencing the velocity of particle 2.